Multivariable calculus, exact differential equations. Now here's something for you trivia buffs. What does this picture illustrate? Navier-Stokes differential equations are used to simulate airflow around an obstruction. So those of you who are going to be engineers, this should be of interest to you. And now a little history lesson from Wikipedia concerning Claude Louis Navier. He was a French engineer and physicist who specialized in mechanics. After the death of his father in 1793, Navier's mother left his education in the hands of his uncle, Emilien Gauthey, an engineer with the Corps of Bridges and Roads. In 1802, Navier enrolled in l'École Polytechnique, and in 1804 he continued his studies at l'École Nationale des Ponts et Chaussées, from which he graduated in 1806. He eventually succeeded his uncle as Inspector General at the Corps des Ponts et Chaussées. In 1824, Navier was admitted into the French Academy of Science. In 1830, he took up a professorship at l'École Nationale des Ponts et Chaussées, and in the following year succeeded exiled Augustin Louis Cauchy as professor of calculus and mechanics at l'École Polytechnique. Now, Cauchy is the one who wrote the brilliant delta epsilon definition of the limit. And there's a statue of Claude Louis Navier. So the topic at hand is exact differential equations. And what are they, you may ask? Well, here's the definition. A first-order differential equation of the form m of xy plus n of xy dy dx equals 0 is exact if there exists a function f of xy such that the partial derivative of f with respect to x equals that first m function, and the partial derivative of f with respect to y is equal to the n function. So here's a little theorem. Every separable differential equation is in fact an exact differential equation. Let's prove that little theorem. Every separable differential equation can be written in the form q of y dy equals p of x dx, which can be rewritten in the form negative p of x plus q of y dy dx equals 0 by subtracting p of x dx from both sides and then dividing through by dx. Now, negative p of x then is our m of xy. It just happens to not contain any y terms. And q of y matches our n of xy. It just doesn't happen to include any x terms. So now we've shown that we can put the separable differential equation in the correct form for an exact differential equation. Furthermore, let f of xy equal negative integral p of x dx plus the integral of q of y dy. In other words, the integration of that left side of the equation if we had multiplied through by dx first. Okay? So then when we take the partial derivative of f with respect to x, the q of y integral just goes to 0 because it doesn't have an x in it, and we get negative p of x. And if we take the partial derivative of f with respect to y, then the p of x integral goes to 0 because there's no y in it, and we just get q of y. And therefore, we have shown that the partial derivatives in fact match m and n as they should if in fact this is an exact differential equation. Okay, let's review the chain rule for partial derivatives. dz dt is equal to the partial derivative of z with respect to x times dx dt plus the partial derivative of z with respect to y times dy dt. This was back in chapter 12. So if we want to look at df dx, that's going to be the partial derivative of f with respect to x times dx dx plus the partial derivative of f with respect to y times dy dx, just substituting x for t in the formula above. And of course dx dx is just 1. So the derivative of f with respect to x is the partial derivative of f with respect to x plus the partial derivative of f with respect to y dy dx. Now why are we going through that? Well, that matches my m of xy plus n of xy dy dx. And so basically that whole thing is going to be df dx. Same form if the differential equation is exact. Okay, and that's why the partial derivatives are important and actually match up with m and n. Now let's talk about solving exact differential equations. Let m of xy plus n of xy dy dx equals 0 be exact, but not necessarily separable, because obviously if it were separable, then we wouldn't need this new method, would we? So here it is again, and we know that it is also equal to, if in fact it's exact, it's going to be equal to the partial derivative of f with respect to x plus the partial derivative of f with respect to y times dy dx. And we know that that is in fact saying that the derivative of f with respect to x is also equal to 0. So now all you have to do is integrate. On the left there, we actually get f of xy, and for 0 we get c. And so f of xy equals c is going to be the general solution. And to find f, of course, we're going to have to look at m and n as the partial derivatives and work backwards, which we've already done in a previous section in this chapter. So all we need to do is compute f of xy, which was called a potential function in section 14.3 of Edwards and Penny. So it's kind of a review of that section in a way, but with a different application. So let's look at an example. Show that 2x cubed y squared plus x to the fourth y dy dx equals 0 is exact, and find a general solution. So there's your m of xy and there's your n of xy. And if it's exact, then the partial derivative of f with respect to x equals the m function, and the partial derivative of f with respect to y equals the n function. So working backwards from the partial derivative with respect to x, we integrate the x term and keep the y squared as a constant multiplier. And there could possibly be a function completely in y that went to 0. Working backwards from the partial derivative of f with respect to y, we integrate the y term and keep the x to the fourth. And of course, there could have been an h of x function that went to 0. But when we compare the two, it's pretty obvious there is no h of x, there is no g of y. And so our f function is just that first term that they have in common. So the general solution is 1/2 x to the fourth y squared equals c. Now, this particular example can be checked by another method. You have to be kind of tricky, but it turns out that you can separate the variables. For example, if I just factor out an x cubed y and then divide both sides by x cubed y, then 2y plus x dy dx equals 0 is going to give us a solution. And we can multiply through by dx and move the 2y dx to the other side, and then move the y to the left and the x to the right, and now we've separated the variables. So now all we have to do is integrate both sides, and that gives us this equation. And to solve that, then we take the antilog of both sides, and then I can rearrange that right side, pull the e to the c out as a constant k, which in this case would have to be positive, and then jump that -2 up using the law of logs. And now my e to the log can cancel, and when I take y out of the absolute value, then I just take plus or minus the other side, and a can just be, positive or negative, and when I square x, it doesn't matter if the absolute value is there. Now, this doesn't quite match our general solution yet, but let me play with it. Multiply both sides by x squared. Doesn't quite match yet, but if I square both sides, now we're getting really close. And a squared could be 2c, and so then if I just divide it by 2, I do in fact get the same general solution. Okay, let's look at another example. Show that the quantity 2x plus y cubed times dx plus the quantity 3x y squared minus e to the -2y times dy equals 0 is exact, and find the specific solution if y of -1 equals 0. Now notice that this time we're not going to be able to use separation of variables to solve this. Okay? So using m, which is the first function, times dx as the partial derivative of f with respect to x, and the second quantity as n of xy, the partial derivative of f with respect to y, we're going to work backwards from the m function. So 2x becomes x squared, and y cubed is just a constant in this, treated as a constant, and so it's just y cubed times x plus possibly a function in y that went to 0. And then working with n, the 3y squared becomes y cubed. We keep the x as a constant multiplier, and then we integrate negative e to the negative 2y to get 1/2 e to the negative 2y, and then there could possibly be an h of x, which went to 0. And of course, looking back at the previous solution, h of x is pretty obviously x squared, and g of y is pretty obviously 1/2 e to the negative 2y. And in common is the term xy cubed. So there is indeed a function f that satisfies these requirements. And here it is. The term they have in common plus the g of y and the h of x. And so our solution then is just to set f of x equal to c. Now, in particular then, they want the solution where y of negative 1 is 0. So we plug in negative 1 for x and 0 for y, and solving for c, we get 3/2. So our final solution is our f function equal to 3/2. And if you don't like that, you can always multiply through by 2 to make it nicer. Note that we cannot solve for y explicitly in this case, so we're stuck with an implicit solution. Okay, this section is not in your Edwards and Penny's text, and so here is a copy of the problems from an Ellis and Gullick text that, if you're in my course, I'll email them to you, and I'll also post them on Google Docs. And here are the answers to the odd problems, so you know what I'm going to do with the even problems, don't ya? Okay, a little humor. Foxtrot by Bill Almond. Word problems, nothing but word problems. Thank you. Farmer Bob's vegetable garden is 20 feet wide by 30 feet long. Calculate its area in square footage. 20, 30a. Okay, I'm going to put that on the Cartesian plane. I'm going to integrate the function, which is just 20, and the antiderivative of 20 is 20x from 0 to 30, and then I use the fundamental theorem of calculus, and I get 600 square feet. Call me Mr. Rigorous. Jason, here's your quiz back from last week. Ha 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 ha. See you next time.